Welcome to Mech Zone. So today we will be starting an all new topic, that is heat exchangers. So today the topic of analysis would be heat exchanger. This is the second chapter. We have finished with the first chapter in which we already studied about conduction, convection, radiation, heat generation, steady and unsteady heat flow. Now we will be discussing about heat exchangers. As the name suggests, heat exchangers are the devices which are used to exchange the heat between hot and cold fluids. They are used to exchange the heat between the hot and the cold fluids. For example, we have a pipe in which there is hot substance which is flowing, such that the mass flow rate of the hot substance is m dot h. H stands for hot substance, kg per second. Okay, such that the inlet temperature of this hot fluid is Thi, and the exit temperature of this fluid is Th exit. I stands for inlet, E stands for exit, H stands for hot fluid. And on the other hand, we are also having a cold fluid which is flowing in parallel. Tc inlet, C means cold, temperature of the cold fluid at inlet, mass flow rate of the cold fluid, kg per second, and TCE. TCE is the exit temperature of this cold fluid. Now there is one assumption, and this assumption is very important, and the assumption is that this process is actually adiabatic, that is delta Q equals to 0. ये प्रोसेस जो है हमारी एडियाबैटिक है. इसका मतलब है इसमें से ना ही कोई हीट सराउंडिंग में लीक करेगी और ना ही सराउंडिंग से कोई हीट इस सिस्टम के अंदर आएगी. सो दिस इज assumption which is to be noted here. And अगर इसका एनालिसिस हम करें तो इट इज एक्चुअली एन ओपन system and steady flow open system. Steady because टाइम के साथ कोई भी चीज का वेरिएशन हमें नहीं देखना है. ओपन सिस्टम बिकॉज क्योंकि इसमें से मास भी एक्सचेंज हो रहा है और इस सिस्टम में मास भी क्रॉस कर रहा है और एनर्जी भी क्रॉस कर रही है. सो इट इज एन एग्जांपल ऑफ स्टेडी फ्लो ओपन सिस्टम. Okay, this is an open system. Now we will only discuss about the basics of heat exchangers, the types of heat exchangers and relative formulas. Okay, now we see again, I'm repeating this, that a hot fluid is flowing in this pipe, say of mass flow rate m dot h, and a cold fluid of mass flow rate m dot c, such that the inlet temperature of the hot fluid is Thi, exit temperature is The, inlet temperature of the cold fluid Tci, and exit temperature of the cold fluid Tce. Okay, so our heat exchangers can be defined as a steady flow adiabatic. It is also an adiabatic system. A steady flow adiabatic open system in which the two fluids are exchanging heat energies between them, such that the heat is being transferred without any gain or lose of heat to the ambient surrounding. Please note that there is no loss of heat or gain of heat from the surrounding. Now if we discuss about these three boiler accessories, that is economizer, superheater and air preheater, then we will find out then that in all the three cases, in तीनों cases में ही the heat from hot flue gases की जो हीट है उसी को यूज करके आगे प्रोसेस में लिया जाता है. इसमें हम लोग क्या हीट करते हैं, हम लोग इसमें फीड वाटर की हीटिंग करते हैं बाय यूजिंग द हीट फ्रॉम द हॉट फ्लू गैसेस. इसमें हम लोग सुपर हीटेड में एक्चुअली हम लोग क्या हीट करते हैं, ड्राई सैचुरेटेड स्टीम को हीट करते हैं. एंड इन केस ऑफ द एयर प्रीहीटर वी यूज द एयर फॉर कंबस्चन. द कंबस्चन के लिए जो हमें एयर रिक्वायर्ड है उसकी हीटिंग करते हैं हम फ्रॉम द जो हीट निकलती है हमारी हॉट फ्लू गैसेस से. और अगर हम कूलिंग टावर की बात करें तो इट इज द biggest heat exchanger. It is the biggest heat exchanger. ठीक है, यहाँ ड्रॉट रॉड का कॉन्सेप्ट आता है जो कि हमें फ्लूइड मैकेनिक्स में हम लोग पढ़ेंगे, ठीक है। दीज आर एक्चुअली द हाइपरबोलिक कूलिंग टावर्स, हाइपरबोलिक कूलिंग towers, and cooling is taking place by means of forced convection by using a fan or a blower or anything। तो एयर को इसमें ब्लो कराया जाता है और कूलिंग टावर से पास करा के हॉट एंड ह्यूमिड एयर को फाइनली निकाल दिया जाता है। ओके, so if we apply steady flow energy equation, steady flow energy equation to this heat exchanger, then we will find that the rate of enthalpy decrease of hot fluid would be equal to the rate of enthalpy increase of cold fluid। हमारा जो हॉट फ्लूइड है वो हीट एनर्जी देगा और जो हमारा कोल्ड फ्लूइड है वो हीट एनर्जी लेगा। तो एंथैल्पी ऑफ द हॉट फ्लूइड तो डेफिनेटली घटेगी और एंथैल्पी ऑफ द कोल्ड फ्लूइड आपकी डेफिनेटली इंक्रीज करेगी। तो अगर हम हॉट फ्लूइड का कंसिडरेशन देखें और उसके करस्पॉन्डिंग हम लोग हीट निकालें, सो दैट वुड बी m डॉट हॉट Cp ऑफ द हॉट एंड डेल्टा T। व्हाट वुड बी डेल्टा T? THI minus THE, THI minus THE, high temperature minus lower temperature. This is in the form of MC delta T, the heat which is being associated with the hot fluid. Now if I write similarly for the cold fluid, I will obtain m dot C, Cp of the C, T cold exit minus T cold inlet, because the exit temperature of this cold fluid is greater than the inlet temperature, and that is why I am writing TCE minus TCI, again using this same funda of MC delta T. Now we know that the amount of heat which is being given by the hot fluid would be equal to the amount of heat which is being taken by the cold fluid, because there is no loss of heat to the surrounding. Here we have already assumed that it is an adiabatic system. Now equating these both to m dot h, Cp means the specific heat of the hot fluid, THI minus THE, that would be equals to m dot C, CPC, TCE minus TCI. Okay, so this is actually the steady flow energy equation which is being applied to the heat exchangers, such that the enthalpy drop in the hot fluid that would be equal to the enthalpy increase in the cold fluid. Okay, now there is one exception. There is one exception. An exception is steam. Exception is steam. For example, if any system is having condensation of steam, now if the steam is being condensed, if there is any condensation of steam, and if we will plot a graph between the temperature versus the entropy plot, okay, now here we have the saturated steam. Now this steam will condense and it will be in the form of saturated liquid. Here it will be saturated vapor, here it will be saturated liquid. So the gap between the 2 points will be HFG, that is the latent heat of condensation. So latent heat of condensation will be the difference between these 2 points. Okay, that is the difference between the saturated vapor state and the saturated liquid state. So if I write rate of heat transfer so if I write down the rate of heat transfer in case of steam, that would be mass flow rate of the steam into latent heat plus sensible heat. Latent heat would be HFG. We know that HFG is equals to Hg minus HF, that is the enthalpy of the saturated vapor minus the enthalpy of the saturated liquid, and plus sensible heat would be specific heat of the water into delta T. So in case of the steam, the situations are going to be different. That is mass flow rate of the steam. This is for the steam. HFG is the latent heat which is obtained from the graph, or the value may be given. Okay, and CPW will be the specific heat corresponding to the water. Now, in order to have the maximum heat transfer rate, the product of mass and specific heat capacity should be minimum. The product of mass and specific heat capacity should be minimum in order to have the maximum heat transfer rate. Please remember this equation, this fact, because it may be directly asked in the examination. Okay, we now come to the classification of heat exchangers, and these heat exchangers can be classified into the following three categories. The first category is direct transfer types. Now, in case of the direct transfer types, the hot and the cold fluid do not have any physical contact. That is, the hot fluid and the cold fluid do not have any physical contact. There is no physical contact between the hot and the cold fluid, but still the heat is flowing between them. For example, this is a copper tube, okay, and in this inside tube we are having the cold fluid and the hot fluid is being supplied from the top. So let us say that H1 is the convective heat transfer coefficient corresponding to this hot fluid, and by means of convection the heat is being convected into this cold fluid. So we can see that there is no direct physical contact between the hot and the cold fluid. So this is a direct transfer type of heat exchanger. The second category of heat exchanger is direct contact type. Direct contact type means it is the opposite of the previous one. That is, there is a direct physical contact between the hot and cold fluids, So this becomes the opposite of the previous one. Okay. Now the third type, that is, we have regenerative type or storage type of heat exchanger. So these are the three types of heat exchangers. Now in case of the regenerative or the storage type, there is actually a matrix and the cold and the hot fluids alternatively pass through that matrix and they exchange the heat. The diagram is quite complicated, so I'm not drawing it. I'm just telling you that it uses a heat matrix. Okay, it uses a heat matrix and hot and the cold fluids alternatively pass through that matrix and they exchange the heat. Okay, now we come to the direct transfer types of heat exchangers, and they are further classified into two categories. पहली category है हमारी parallel type. Second category है हमारी counter type. Parallel type flow. Second is the counter flow, and third is the cross flow. So we will start with the first category, that is parallel flow type. We start with the first category, that is the parallel flow type. Now in the parallel flow type, it is very easy to understand. There are actually two pipes. Okay, no, there are not two pipes. Actually it is one system, such that in the middle portion we are having some partition, say separating wall. On one side we are having the hot fluid and on the bottom side we are having the cold fluid. We are having this cold fluid. So there is actually a heat flow between the hot and the cold fluid such that the inlet temperature of the hot fluid is Thi, exit temperature The, inlet temperature of the cold fluid Tci, and exit temperature of the cold fluid Tce. Okay, so these are the entry and the exit conditions. What we are observing here is the direction of flow of the hot and the cold fluids both are same. They are flowing in the same sense or direction. Now the second type, that is the counter flow. Counter flow. In case of the counter flow, the same thing happens, but the direction of flow of the hot fluid is this, and the direction of the cold fluid would be opposite to that of the hot fluid. So this is Thi, Th exit. Here we will have Tc inlet and Tc exit. Okay, this is the direction of flow of the hot fluid, and this is the direction of flow of the cold fluid. So it is the opposite. Okay, it is the opposite as the case we have discussed just before it. Now third case, that is cross flow. Cross flow is nothing but, say the direction of hot fluid is like this. This is hot fluid, and the direction of the cold fluid will be like this. This is the cold fluid. So this is a cross type of heat exchanger, that is cold fluid is getting into it and the hot fluid is getting into it from this direction, therefore making a cross. They are making a cross. So this is actually a cross type of heat exchanger. Now if we try to draw the temperature profiles of the parallel heat exchanger, counter heat exchanger, then what will be observed? For example, now we know that the temperature of the hot fluid will keep on decreasing, and the temperature of the cold fluid will be keep on increasing. So if we start from Thi, that is the inlet temperature of the hot fluid, and here at some point we will have Th exit, that is the exit temperature of the hot fluid, it would be like this. Okay, now at some point we are having temperature of the cold fluid at inlet and temperature of the cold fluid at exit. It will be like this. So this will be the temperature profile of the hot and the cold fluids, and this will be delta T, and this will be delta T. Now we can see that Tce can never be greater than The. Tce can never be greater than The. Okay, now this was for the parallel heat exchanger. Now we have for the counter flow heat exchanger. Counter flow heat exchanger. Now in case of the counter flow heat exchanger, this is the temperature of the hot fluid at inlet and temperature of the hot fluid at exit. So it will be like this. Okay, now we have temperature of the cold fluid at exit and temperature of the cold fluid at inlet. It will be like this. In the above diagram, the direction of both the fluids was same, but now here the direction of the hot fluid is like this and the direction of the cold fluid will be opposite to it. This becomes the delta T, that is the temperature difference. Okay, so in reality, let me tell you, these are not parallel curves. So as I was discussing, these curves are not parallel. In reality, these curves are not parallel curves. These curves are not parallel curves. Okay, so these are the temperature profiles in case of parallel and the counter flow. Now if we observe and analyze the delta T in case of parallel flow is actually greater than the delta T in case of the counter flow. The delta T in case of the counter flow is less as compared to that of the parallel flow, and we know that the variation of temperature actually is taking place with respect to the x, that is with respect to the x direction, and this variation in the temperature is much more pronounced as compared to the counter flow. So as the temperature difference is more, we can say that parallel system is more thermodynamically irreversible. It is thermodynamically irreversible, and this counter flow system is much more reversible as compared to the parallel flow system, because in case of the counter flow system the delta T is very much less, hence irreversibility in counter flow is less and irreversibility is much more in case of the parallel flow systems. If we write the expression for the heat transfer, that is dq is equals to UA delta T. Now यहाँ पर U क्या है? U है हमारा overall heat transfer coefficient, overall heat transfer कोफिशिएंट, और हम लोग ओवरऑल हीट ट्रांसफर कोफिशिएंट तभी यूज करते हैं जब हमारे सिस्टम में एक मोड से ज्यादा मोड हीट ट्रांसफर के हो रहे हो, जैसे फॉर एग्जांपल कंडक्शन भी हो रहा हो और कन्वेक्शन भी हो रहा हो. A is the area of the heat exchanger, delta T is the temperature difference. Now one very interesting fact to be noted here is that TC exit can be greater than the T hot exit, but only in the case of counter flow. Only in the case of counter flow heat exchanger. Okay, so T cold exit, that means the exit temperature of the cold fluid can be greater than the exit temperature of the hot fluid, but only in the case of the counter flow, whereas this is never possible in case of the parallel flow. Now we will introduce a new term, that is mean temperature difference. Mean temperature difference. Okay, now it is a parameter which takes into account the variation of delta T with respect to x. We know that as the distance is increasing or as we are moving, the temperature is varying with respect to x. So this is the factor which is taking into account this variation of temperature with respect to x or along the x direction. Okay, so we write Q equals to UA delta T mean, where delta T mean is the mean temperature difference. Now we will not derive the expression for this mean temperature difference, but rather I am going to write it directly, because that is not in our scope of syllabus. The direct formula is useful, that is delta T mean is equals to 1 upon A integral inlet to outlet delta T dA. So this is the expression for the mean temperature difference. Okay, this is the expression for the mean temperature difference, that is 1 upon A from integral inlet to outlet delta T dA. This is the mean temperature difference formula. Okay. Okay, we will now discuss about one more parameter, that is logarithmic mean temperature difference. And let me tell you, logarithmic mean temperature difference, I am directly writing out the formula because derivation is not at all important. Formula is theta 1 minus theta 2 whole upon ln theta 1 upon theta 2. This is the formula for the logarithmic mean temperature difference. Now I'll be discussing what is theta 1, what is theta 2. Okay, now for example, if we have the temperature profile for the parallel flow, this is TH inlet, TH exit, T cold inlet, T cold exit. Okay, the difference between these two temperatures is θ1, the difference between these two temperatures is θ2, if this is the parallel heat system, heat exchanger system. Now if we have counterflow system, then we will get TH inlet, TH exit, T cold inlet, T cold exit. This will be the difference between this and this is θ1, and the difference between these two would be θ2. We will simply keep the values of θ1 and θ2 and we will determine the logarithmic mean temperature difference.